see here. So I'll begin with a scripture. This is Habakkuk. It's not an easy one to say. Chapter 2, verse 14. For the earth will be filled with the knowledge of the glory of the Lord, as the waters cover the sea. So I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to help us to use this time wisely as we review for Test 1, Lord. In your name I pray, Lord Jesus. Amen. I don't seem to be able to talk today. That might be a problem. But anyway, let me, so you guys gave me your mission 3, which is wonderful. I will soon give them to the grader. And hopefully they'll get them back to you. But they won't be back to you before the test, right? So if you do need to scan that to compare it to the solution, after now, you're welcome to take pictures of your mission 3 and give it back to me, all right? If that's something you want to do. If it's not, whatever. So problem 1, this is actually a pretty good problem in terms of reviewing for the test, because it's got a good number of ideas in it, which is to figure out whether or not two vectors are in the span, a vector is in the span of another pair of vectors. The easiest thing to do, of course, is to put them in a matrix, row reduce it, and then you can look at the reduced or echelon form. And so for this one, VW and B1, we can look at the first 3 columns here. We can see column 3 is twice the first column minus the second column. Then by the column correspondence property, the same pattern must be true for the original matrix, which gives me that B1 is 2V minus W, which means that B1 is in the span. All right, so you should know what the span is. The span is the set of all possible linear combinations of the given set. And on the other hand, it is also clear from the reduced or echelon form here that the 4th column is in no way a linear combination of the first 2, right? See that? If we look at these 2 and then that, well, that's just E1, E2, E3, which is, by the way, linearly independent, which is to say there does not exist a way to form the last one as a linear combination of the first 2, among other things. So in that sense, I can see immediately from the final matrix here that column 4 is not in the span of columns 1 and 2. And then by the column correspondence property, the same is true for the original matrix, which by our construction tells us everything we need to know about VW, B1, and B2. Now, is this the only way to do this? Certainly not. You could write out systems of equations and work them out. But here I think I said specifically to use the CCP to try to get you guys to learn this stuff. But anyway, there's that one. Next here, this one is just a little bit sneaky because I didn't just tell you the pivot columns, right? I gave you a non-pivot column and a pivot column and another pivot column. So you kind of had to solve for the pivot. And then once you solve for the pivot, you can easily find the 5th non-pivot column like that. All right, so again, the column correspondence property gives you the necessary interlinking identities between the columns, which you then can reconstruct A, right? Sort of a forensic problem here. Let's see here, this one, pretty straightforward. You just row reduce this thing, and eventually I got to this thing right here, all right? And then I was asked to write the non-pivot columns as linear combination of the pivot columns. Again, looking at the reduced or echelon form, I can immediately see that the 4th column is the sum of the 1st, the 2nd, and the 3rd column, and I can immediately see that the 5th column is the difference of the 2nd column and the 1st column. Then by the column correspondence property, the same linear dependencies must be seen in the original matrix. So there they are. That's part A. Part B, you just write down the pivotal variables as being dependent on the non-pivotal variables, which appear as free parameters. Here, columns 4 and columns 5 are free, are non-pivot columns, therefore x4 and x5 are free parameters, which means we have the exciting equations x4 equals x4 and x5 equals x5 appearing in the 4th and 5th slots here, whereas the 1st, the 2nd, and the 3rd are more interesting. For example, the top row there tells me that x1 plus x4 minus x5 is equal to 0. Solving that for x1 puts a minus on the x4 plus on the x5. Likewise, the 1, 0, 1, 0, 1, 1 gives me this right here. And then finally the 0, 0, 1, 0 gives me that minus x4 there. And then we factor out the free parameters, like so and like so, the vectors that remain will be the basis for the null space of A. All right, that's the procedure. Row reduce the matrix, identify the defining equations, write them into the vector solution for AX equal to 0, and then factor out the free parameters. What remains, those two vectors, will by necessity be linearly independent, and they will form a basis for your null space. That always happens. Unless, of course, your null space is just the 0 vector. It's something I haven't talked about, because this is 320, listen to me, this is 321, this is 221. Like, what is the basis for the 0 space? That may not even be in your notes. But by convention, the span of the empty set is the 0 vector. So if you're wondering, like, logically what goes in there, we by definition say that the span of the empty set, the set containing nothing, is a 0 vector. That makes our theorems and so forth logically consistent. But if you find yourself saying that the basis is the empty set in here, that means I have messed up a problem, because that's not something I would ask in here, okay? That's a 321 thing. I just mentioned it for your idle curiosity, supposing you have some. Now, you do. All right, some of you more idle than others. Some of you more curious than others. I really don't know. I'll know after I grade the test. Okay, so then this one, find the inverse. We do the usual thing. We make the super augmented matrix with the identity matrix, right? Do my row operations. I get this lovely matrix of fractions. And then to solve for x, I multiply by A inverse, which gives me that, which you could also write like that. Yeah. Problem 35. Again, make the super augmented matrix, row reduce that thing. What appears in the second block will be the inverse, and there it is. Of course, we could check our work. Yeah, what'd I do?
For 34, I think the second solution is C over 3, not B over 3.
Oh, yeah, definitely. Thank you. I will try to fix that. Yep. Anything else? See, I haven't checked my work with anybody, unlike you guys. Because I did this last night between, well, let's not talk about it. I wanted to get the full engineering experience, you know? Completing the homework like less than a day before it's due, you know? Something like that. Feel the danger. So I'm sorry I have neglected, I have failed to show you guys the steps. I hope you did put steps in here. There aren't too many steps. I think it's like 4 row reductions or something, 5 maybe, to get that one right. We are soon coming to the portion of the course where I don't expect you to show all the row operations every time. All right, but I will say as much when that happens. Until then, you assume you need to show row operations. Certainly on the test you need to show row operations. Unless you could just guess the answer. Guessing is a method. Sometimes it works, right? Anyway, again, the super augmented matrix, row reduce it, you get to that, which shows you that the inverse is this right here, and then multiply by the inverse, and you get 57 minus 28, 15 minus 6, and 5. By the way, if you were just after the solution of AX equal to 1, 2, 3, 4, 5, this is a stupid calculation, right? What's the better calculation? So there's this unfortunate thing that happens in this course is we talk a lot about inverses before the test, and some of you will get it in your head, I need to use inverse to solve everything. This is wrong. This is very wrong. You should only use inverse if it's asked of you, almost certainly, because it's way, way, way faster to just take the matrix which is given, to slap 1, 2, 3, 4, 5 in the 6th column and just row reduce that. You'd immediately get this solution much faster. You wouldn't, have to write nearly as much, right? That would be like 60% less calculation, something like that. Or like a problem that you don't not get done on the test, Time is money on the test. So so it's important not to just think about, knowing I can do that problem does not suffice in here, right? I can do that problem in an efficient and wise way is what you must come to in here, right? Pretty much anybody, given a linear algebra problem, given sufficiently much time, you know, and maybe money, some kind of carrot, certainly can solve it. It's linear algebra. It's a system of linear equations, right? The issue is, can you solve it wisely? Can you solve it efficiently, right? Can you use the theory that we've talked about to actually solve problems? This one here, I kind of gave you guys a huge hint. So we Sachs-Schutz identity for the inverse, and then remember we proved that the inverse of the transpose is the transpose of the inverse, and then, yeah. Now, if I hadn't given you that hint, this was a less friendly problem, wasn't it? As some of you experienced without the hint, right? But you could still do it. Problem 38. Here, the method of calculation that we used in the previous two problems is no longer relevant because you don't have specific entries for the vectors. We have to approach this symbolically. And as such, we look at the problem of finding a 5 by 5 inverse as the problem of solving 5 independent linear equations within in homogeneous terms E1, E2, E3, E4, E5 separately. And I'm just calling the columns of the inverse I'm interested in W1, W2, W3, W4, W5 because they need a name. And then I just go about taking the given data and, like, you know, adding, subtracting, and doing various things to try to eliminate things I'm not interested in, right? I'm after just having just an E1 or just an E2, you know, just an E3. Once I have that, then I can say, oh, well, that's my W1, that's my W2, right? So like this one, adding these two equations made the E2s cancel. I got two E1s. So if I, like, you know, solve for E1, I get A times this vector is E1. Likewise, A times that vector is E2. Now the V4 and V5 requires a little bit more sneakiness, but the same idea basically holds. Multiply by sine, multiply by cosine. The sine cosine terms cancel, and you get sine squared plus cosine squared. That gives you a W4. And similarly, multiplying by cosine and sine will eliminate the other terms and give you a solution to E3 there. And oh man, I think I mixed. Yeah, I mixed it up, guys. Look, so this is a typo at the moment. I should have done what? You might not be able to see it, but this and this should be flippity-flopped because this was the E, where was it? E3 was the difference, so that should be this one because it's the third column. And that should be over here. My bad. So I'll try to fix that typo currently. I was trying to give you one of these in class as an example, but the stupid thing I wrote on the board in class was like too simple. Like there was nothing to solve in my class example, but this is kind of more interesting. Now, some of you have solved problem 39, and you've got a right solution, but you have a wrong solution. The reason you have a wrong solution is you did not multiply by the inverse, because multiplication by the inverse is just much faster than anything else for the 2x2 system, unless what? Unless the 2x2 system just allows elimination by, like, adding equations, right? Then that's faster always. But for an ugly 2x2, multiplication by inverse is pretty hard to beat. You should know the 2x2 inverse formula. That's something we know. I expect you to know it, memorize it, right? Any questions? You guys can jump in whenever you want. Problem 40, some of you have got a lot more calculation than I do here because you misinterpreted the problem to say calculate the inverse. I did not say calculate the inverse. I said show what values of k make A inverse exist, which is a different question. To do that, all you need to do is look at the row reduction of A and come to an understanding of when or not it can reduce to the identity matrix. If it can reduce to the identity matrix, that means that the columns of A are linearly independent, and hence the inverse exists by our multi-part theorem. And if k is equal to 2, it's not possible, because if k is equal to 2, that means that the third column is a linear combination of the first two. Check it out. 2 plus 0 is 2, 1 plus 2, 3, 1 plus 3, 4. If k equals 2, we're out of luck. Yeah? So, yeah. Oh, nope. That was a glass adjustment, not a question. Okay. Problem 41, you know, not especially interesting, but kind of fun. I think odd problems in the book are always fun, right? because they have answers. Yeah. But that block multiplication gives us these 6 matrix equations, which we can pretty much just straight solve by multiplication by inverse, as in my x and my y equation. Once I have the x and the y equation, actually I don't even need the y equation. Once I have the x equation, I just plug it into the star equation, and that gives me this as the answer. Yay. Now, problem 42. I think in the heat of battle last week, I gave some of you not the best advice. And the not the best advice was to not pay mind to my instructions. My instructions explicitly say, calculate A inverse and B inverse, the 2 by 2, right? And they say, and then check via block multiplication of the partition matrix M, that M inverse times M is equal to the identity. I said use block multiplication, but I let so many of you go down the garden path and do scalar multiplication, as I have right here. Scalar multiplication, like the full 4 by 4, all 16 entries multiplied out, right? Do. Of course it works out, right? But this was not my intention. My intention was for us to follow the instructions. What do the instructions say? Check with block multiplication, which I have over here. It's way easier. It's just so much easier. See, this is block multiplication. M is A0, 0B. M inverse is this, allegedly. Multiply it out. Here's your individual block matrix equations, which of course simplify to identity 0, 0 identity, which is also known as the identity. Of course, we could be more precise and put down sizes of matrices, right? Like technically, this is I2, 0, 2, 0, 2, and this is I4 if you're keeping score. Now, I will tell the grader not to take off points here because obviously that would be kind of mean if I did. So if somehow this fails to be communicated to the grader and she takes off points for it later, come back, tell me about it. I will give you back those points. I bet I wrote less than you did. So problem 43, the ijth component of M transpose M is the ith row of M transpose dot product with column J of M. But what is the ith row? It is Ui transpose. What is the jth column? It is Uj. What's the dot product? U transpose times Uj. Anyway, that's given to be Kronecker delta Ij. It's either 1 because the vector has length 1, so dot product of a unit vector with itself is 1, or it's 0. That's the Kronecker delta. Also known as the components of the identity matrix. So this gives me M transpose M equals to the identity, which then tells me that the transpose is the inverse, which is that. So I'm sure if I was in your shoes, if I was a student in this class, I would have found a way to write a page for that. Because when I was where you guys are, I wrote everything out in components, whether I needed to or not. You know, because it was kind of like a safety blanket. It made me feel like I knew what I was doing. But in fact, I didn't. Well, I mean, I guess I did, but I was doing it slowly, at least. Anyway, here's the LU decomposition problem from Yield book. They give you the LU decomposition. You're supposed to use it. So basically, the idea there is to make a substitution. Y is equal to the upper triangular matrix times X. Solve the Ly equal to B problem, like so. You get Y is 1, 3, 3. And then you solve U, X equals to Y, like so, which gives you X equals to minus 1, 3, 3. And so there's the answer. Of course, there are two answers here because the book gave us instructions to find both the Y and the X, right? Why did it do that? To keep you guys from just solving the system straight out, right? And ignoring the LU decomposition altogether. Which would be totally legitimate here because this problem isn't really complicated enough to warrant the LU decomposition. This is a toy example. To really appreciate the LU decomposition, I think you need much bigger problems. Or you need to be thinking about that application to, circuits that's in the textbook. But nevertheless, this is a well-known factorization technique, which you should be aware of as students of linear algebra. And I hope that now you're aware. By the way, I did not find enough time in the weekend to fix the permutation issue. So sadly, there will be no video. You're free to go on with your life and ignore the permutation issue. It won't happen in this class. If it does, then I made a mistake or something. Which is not to say we're not covering LU decomposition. I'm not saying that at all. I'm just saying that the LU decomposition that we will cover is the one that doesn't involve a row swap, all right? Which I will admit is a little bit specialized. So anyway. So here, last problem, I did my row operations, right? And when I did that, I put the 3 there, I put the -1/2 there. My third row operation, I subtracted twice the second one from the third. That puts a -2 here, at which point I'm done. See, because from that I can read my identity matrix padded with the 3, -1/2, -2, and then what's left there, ignoring the parenthetical things, is this. And that indeed is the LU decomposition for this matrix. The L will always be rectangular, listen to me. The L will always be square because it's nothing more than the product of the elementary matrices that formed the row reduction inverted, which is why we're putting, not -3 but +3, not +1/2 but -1/2, not +2 but -2, because to do the opposite of the row operation just requires changing that second number from plus to minus or minus to plus. That is the inverse operation. And as I think I've kind of showed you the derivation, if you think about what goes on, all you're doing really is you're getting, E3, in this one, E3 times E2 times E1, A is equal to, the upper triangle. It's kind of an REF. It's a reduced echelon form, certainly not a row reduced. We don't even care about rescaling the pivots even, right? And so if you take that, you solve for A, it gives you A is equal to, E1 inverse E2 inverse E3 inverse, I believe. Yeah. Times U, right? But this right here is the L. And so that's why the parenthetical thing that we're doing works like it does, is because it's just being formed by the product of the inverse elementary matrices, which to get those, you just flip the plus to a minus for the row operation is all. And it's just this, as long as there's no permutations. So anyway, and so that's it for this one. What would you guys like me to do with the rest of the time? We got about 20 minutes. 25 minutes. I can go back to the other solutions, to the other missions if you'd like. Should we do that?
Could you go over problem 24 from mission 2?
I can do that. If I can find it. Let's see here. I do like problem 20 for a test question, but if I did ask 20 as a test question, I want it to be more interesting. I don't want the answer to every single stupid part to be like, nope, can't do it, nope, can't do it, nope, can't do it. I did intend at least 2 of these to work out, and I made a typo or something stupid. I think I was thinking oh, well, these will be both making sense, but then it didn't dawn on me, oh, you dummy, that's a 2x2, that's a 4x4, you still can't add them, Anyway. You asked me about 24. Yeah, this is a good question. So what do you have a particular question about it, or?
I was wondering if you could go through your process of solving it.
Oh, sure. So what condition must be given for ABC that, ABC is the vectors in the span of V1 and V2? So the solution process. Now, since we did this, we have gained new wisdom as well, right? Let's see, because now we have the column correspondence property also coming to bear, which means that there's an update to the solution, right? We can look at the solution in new light, but I'll look at it in the light which it was originally given to start with. So to start with, what is the span of V1 and V2? It's all possible linear combinations of V1 and V2, right? So I get C1 V1 plus C2 V2 equals to ABC. That's the system, that's the equation I'm trying to solve. But remember, we can rewrite C1 V1 plus C2 V2 as the matrix V1 V2 times the vector of unknowns C1 and C2. Okay? Now, of course, v1 and v2 are specifically given here to be 1, 2, 2, and 0, 1, minus 1, right? They're column vectors. And so this is a system of linear equations. It has that as its augmented coefficient matrix. I did row operations until I got to like this, which is enough. Like I don't feel the need to necessarily get to the reduced or echelon form every time. If I get far enough that I can clearly understand what the solution structure is, I don't feel the need to, you know, rescale this to 1 and clear out. Like I don't need to do that. So anyway, once I get to here, you can see that the system is going to be inconsistent if this last term, which is the inhomogeneous column, is non-zero. If this is 0, it's fine, because then we've got consistent equations, of which there are infinitely many solutions, I think. Oh no, my bad. There's just one solution here, dummy. Me, not you. And so it's consistent only if minus 4a plus b plus c is equal to 0. And that's the condition we need for ABC to be in the span. Of course, you can say more, right? How is ABC in the span in that case? Like, if we're granted that condition, we've got the matrix V1, V2, ABC equals to what? 1, 0, 0, 0, 1, 0, 0, 0, 0, A, B minus 2A, right? 0, right? So that would specifically tell me that ABC is equal to A times V1 plus B minus 2A times V2. So I didn't ask for that in this problem, but that's a nice follow-up comment to this problem. How do I know that? There's two different ways to look at it, right? The first way that we would have looked at it is I'm just saying, oh, C1 is equal to A. C2 is equal to B minus 2A. And I merely plug in C1 and C2 into the original linear combination. And that's a fine way of thinking. But there is another way of thinking, which is the column correspondence property, which just points out that, oh, column 3 is A times column 1 plus B minus 2A times column 2. Therefore, column 4 has to be equal, column 4 is ABC, has to be equal to A times V1 plus B minus 2A times V2, because that is the linear combination which we can see in the row reduction. So there's two ways to think about it, either by the column correspondence property or by just direct solution of the star equation I wrote to start with. There's really not much difference between the two modes of thought for this problem. Like, you could go either way and you'd be right, okay? There will be some problem on the test where I force you to use CCP. So if you're not comfortable with it, there will be problems that you can still solve without it. But there will be some where you're just not going to be able to function without the CCP. Because it is something I want you guys to learn. Now, for part B, the question is, you know, is V1, V2, and this vector linearly independent? Now, we had a definition which was equivalent to the following, that it's linearly independent only if a linear combination of the vectors equal to 0 forces the weights, the coefficients, if you will, in that linear combination to all to be 0. So essentially, you can look at that as a system of equations with you know, variables C1, C2, C3, which has augmented coefficient matrix, the first 3 columns here, and then you've got zeros. But we already did the calculation. See, it's the same row reduction as part A. So you know that the column of zeros at the end just rides along. We get the same silly calculation. And the squiggle just means row operations, which are obvious, which I don't feel like writing down. You can do the same if you're confident that you're right and that you don't really care about the partial credit for making a mistake and not showing the work. Squiggle is, it's like Esther going before the king or something, you know. It's a little dangerous, but it does have its purpose. I'm not trying to say that you should like dress fancy for the test or anything by that, but let's see here. So we need the condition that minus 4a plus b plus c is not equal to 0 in order to make this non-zero and be able to clear that out. If that doesn't happen, then we can't do that, and that means that the last row is zeros, which means there's infinitely many solutions. And if there's infinitely many solutions, that means in addition to the zero solution, there must be a non-zero solution. And a non-zero solution to this equation right here is tantamount to there being a linear dependence amongst the vectors. And if there's a linear dependence amongst the vectors, then it's not linearly independent. So in short, linear independence demands the opposite condition, namely that minus 4a plus b plus c is not equal to 0. But you could have logically said that without further calculation on the basis of a. I didn't need to do all this. I wanted to give you guys a self-contained calculation here, so I did. But truth be told, once you know that the third vector is linearly dependent on the first two, given that condition, you know that condition is death to linear independence of those three vectors. So you simply say not equal to 0 implies linear independence. There's a dichotomy. Either a set of vectors is linearly independent or it's not linearly independent. Not linearly independent is linearly dependent. So there is logic we could use to like truncate this calculation if you wanted to.
Thank you.
Uh-huh. And at this point, we didn't know the CCP. That's why I'm not talking about CCP, right? Those are fun, aren't they? I think these are fun. But anyway. Let's see here. Anything else I should tell you guys? I hope everybody's good on actually finding the elementary matrix. If you somehow missed it, it's not a big deal. All right, so go back and study it again. Like you just do the same row operation to the identity matrix, and that gives you the elementary matrix you want to. The elementary matrix whose left multiplication by A achieves the same row operation on A as the row operation directly. Let's see here. I don't know, you guys have to ask questions, otherwise I'm just going to spin my wheels here. Oh, we could go back and look at an old test. Why don't we do that? Do I have any old? Yeah.
I was going to ask a question about the old test.
Oh, well, what do you know? Which one?
Test 1 from question 12.
This isn't a Rickroll, is it?
No.
Okay.
Problem 5.
Now, the course has changed a bit since I taught it here, so there might be, I wouldn't necessarily, oh yes, this problem. Okay, what about it?
I was just kind of, like, I was confused how to start when it meant, like, make a substitution. Like, I wasn't understanding for this problem what you meant by that, I guess.
Let's see here, do I have, oh, did I ever show you guys my art?
No.
I've never shown you my art. I should show you my art. Let's see here. Whee! Oh, wait a minute. Maybe. All right. Let's see here. I'm hoping I put a problem in here. I think I want to say I had. Maybe I didn't. Was it in the homework? I know I have covered. Maybe it's mission 1. Maybe it was mission 1. I know somewhere I did this. Let us not forget, mission 1 is on the test, right? Yeah, I mean, I'm not talking a lot about writing down augmented coefficient matrix and doing raw operations and solving systems and writing down the solution set, not because it's not important, but because I believe that part you guys are pretty solid on. And as such, it does need to be on the test. It's like the core of this course, right? So don't mistake my silence for some kind of... where'd that thing go to? Oh, here it is. So problem 12 is kind of the same kind of animal. Now, so in problem 12, I didn't do what you're asking me about, though. See, what I did in problem 12 was I just decided to operate at the level of the squared variables. But if you look at what I'm doing, it would be equivalent to like saying y1 equals x squared, y2 equals y squared. If I did that, this would be like y1 plus y2 equals to 4. y1 minus y2 equals to 1. Then I'd have a linear system in y1 and y2, which I could use linear methods for. But rather than doing that in the homework solution, I just added directly because I thought it was more to the point. And like, maybe that substitution isn't really needed. Now, if I've got a linear equation, here's one. Let's suppose some evil instructor gave you something like cosine theta plus sine beta minus, tangent delta equals to 3. 2 cosine theta minus sine beta plus 42 tangent delta equals to 0. Find all solutions to this, Well, then I would suggest maybe, rewriting this as x plus y minus z equals to 3, and 2x minus y plus 42z equals to 0 is maybe a good way to not go nuts. Because then you can go, oh, okay, well, this is, 1 minus 1, 3, 2 minus 1, 42, 0, which is what? 1, 1, minus 1, 3. Subtracting 2, I get 0, minus 3, and 45? Oh, 44, thank you. And apparently, I can't do math. Minus 6, thank you. Well, anyway, you can go on. But the point is, you do this, and then that would tell you, what x and y are. And then you unsubstitute. You put back, oh, well, that means x, the cosine theta, the sine beta, the tangent beta. And then you'd be like, why have you done this to me? Now I am in some sort of pre-calculus, realm of unknown things. Now, that didn't happen here, no pre-calculus, right? We just have to be aware of the fact that we get a square root property gives you plus minus solutions, right? But I did have one in the notes. I did have one in the homework, which was a little bit less. And this one's nice, right? Because it's literally 4 solutions, which you can view geometric. The homework problem is geometric, right? Because it's the ellipse and the hyperbola. There's 4 solutions. When we have 2 equations and 2 unknowns, we don't get 4 solutions if they're linear. We get how many? 1 solution, no solutions at all, or infinitely many. Them's your 3 choices, always, since we're working over a field of characteristics 0, whatever that is. However, if you make a substitution, then all bets are off, because you're not solving a linear system anymore. You're solving something that has the appearance of a linear system, but with that substitution, it's not technically speaking a linear system. So all of our theorems are kind of like out the window once we make a substitution. Like this one, I decided to, again, my bad, I haven't actually made an explicit substitution. I've just decided to do algebra at the level of sine and cosine, because it's just easier. So does that make sense for that? Yeah. Other questions? But that's what I was talking about there, just like introduce a variable. You go back to the test, if I can find it. So I think if you look at that, oh wow, that's reciprocal, that one's fun. So their homework had this stuff in it though. That's the difference between this class and yours. What was C about? Did I have 3 variables? What was this problem? Oh, A and B are arbitrary. Ooh, nasty. I don't think I'm this mean anymore. Maybe I'm losing it. Maybe I can still prove my worth Wednesday, though. I don't know. We'll see. It's all right. I've got nothing to prove. Well, you probably don't have anything to prove. Like, what would be a reasonable proof in here? The one that comes to mind, I think there's really only one derivation I'd like you to know, which is the CCP. That's pretty much it in terms of driving something in here. Because maybe that, or something that you did in your homework, which was what? You proved that the trace of AB was equal to the trace of BA, so that's a question that might appear on the test. Or something similar to that. But that wouldn't be a big part of the test, right? The large part of the test will be calculation. So now the other part of the test, besides calculation though, there's also interpretation, right? So you need to know what to do if I give you something like, a given, row reduction, how to interpret that, right? We've had a number of different problems, either thinking about span, linear independence, or just, the reverse engineering the matrix problem. So anyway, no questions? Yeah.
Are the solutions in the mission to be posted?
They're not. They're not yet?
I didn't see them in Canvas.
1 and 2 are? Okay. But they may not have been when you looked, Gideon, so but yeah, they should be. I need to fix the solution to mission 3 before I post it, because you guys found a couple typos for me. Thank you. Other questions? No one's going to ask how many questions on the test. This is a glorious day. The first time ever.
How many questions?
No! Enough. No, one question. There will be one question on this. Just one question. No, I'm not going to do that, because if I do one question, it's just going to be A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Yep.
One of the old tests says you're allowed a 3x5 card. Are we still allowed that?
Oh, no, there is no 3x5 card. There is just you in the test. That is it. 3x5 card gives a false sense of security, which leads to poor performance. I am not allowing it this semester. I want to see if it helps. So you need to learn the stuff. There's really not much to remember in here besides row reduction and sock shoes identity, but it's the same for the inverse and the transpose, right? I guess the rules of matrix algebra you need to know, but do you know like the laws of arithmetic? I hope so. And what's one other additional idea? You cannot do what? Commute things, right? So one final example for you guys. Let's do something a bit ugly. Suppose I've got a plus bcx equals to, I don't know, ay transpose. Solve for x given B inverse and C inverse exist. Can you do it? Transpose both sides. All right, so this gives us A plus BCX equals to A Y transpose. Great. Then what? Subtract A. I like it. All right, then what?
Inverse of B, then C.
Yeah, multiply by inverse of B. And see, the thing that you guys will get wrong here is you don't sometimes distinguish between left and right. All right, but we multiply by B inverse on this side, we get CX is equal to B inverse times, oops, my bad, A Y transpose minus A, right? And then X is equal to C inverse B inverse times A Y transpose minus A, and like, there you go. Unless I had more information, that would be how it goes. So you should be able to solve that kind of problem, which basically just means understand you cannot commute matrices. You must make a distinction between multiplying on the left, multiplying on the right. need to know how to find an inverse, you need to know the CCP, and I suppose you need to know the LU decomposition. But I don't think that's too much, actually. So, I will shut up.